The next invited speaker is Dr. Zhao. The title of the talk is Developing Trustworthy AI for Autonomous Driving. Professor Zhao is an assistant professor of mechanical engineering in the College of Engineering at Carnegie Mellon University. He's also at the Robotics Institute, Machine Learning Department in the School of Computer Science at CMU too. In directing the SAFE AI lab, Professor Zhao aims to develop verifiable, explainable, and good for all AI for robotics in the race of their uncertain, dynamic, time-varying multi-agents and possibly human-involved environment by bringing statistics and cybernetics. Professor Zhao got his PhD from the University of Michigan, Ann Arbor. And Professor Zhao is recognized nationally and internationally for his research on autonomous vehicles and smart cities, which synthesize methods in machine learning, robotics, and design. His group develops rigorous test methods to verify AI-powered robots and learning approaches that model the operational environment with big data to support vision and decision-making development. Professor Zhao's research has been granted by NSF and Department of Transportation and Department of Energy. He also works with the leading self-driving companies around the world, including Uber, Toyota, and Bosch. Methods and tools developed by his lab are being used by the industry and regulation institutes. And he also received the NSF Career Award in 2021. Okay, whenever you're ready.
Yeah, thank you. So today we'll talk about how we can develop generalizable trustworthy AI for self-driving cars. So I'll go a little fast. I do have a meeting after this. AI has been used for autonomy for a while, and however, it has not been really used in some consequential domains at large scale. One of the concerns is trustworthiness. So our lab at SMU is trying to develop this kind of safe AI for, say, mobility and healthcare. Our mission is to develop trustworthy AI by bridging rigorous theories and practical technologies. So in today's talk, I will mainly our lab mainly focus on the generalization, safety, and robustness of the autonomous vehicle and how we can evaluate and certify those in intelligent autonomy. And in this talk, I will mainly talk about how we can generate some digital twins for safety critical scenarios, and also how to develop robust, safe, and generalizable reinforcement learning. I'll mention a little bit about evaluation and certification as well. So all the papers here, you can check my website. So evaluation, I think, is the bridge between this I call the intrinsic feature of safe, trustworthy reinforcement learning, and also some extrinsic where we have other requirement from human, for example, privacy, the fairness or explainability, which also are important, but I'll focus on those topics today. So simulation has been used and developed a lot in the industry and in academia. This workshop actually also provide a platform. So some of our recent work has been summarized in these two papers. One of the survey on safe critical driving scenario generation. And we have three generative methods I'll talk about today. And also we have a corresponding safe benchmark on this topic, and it's currently under review. We built the benchmark using the Kala open source platform. So why we care about safe critical scenario generation? Because they actually actually very important, but also sparse. So look at the left side of this figure that you can see people need to drive a long distance to collect safety critical events. And actually the more the safer you are, the harder you'll collect those safety critical scenarios. So which makes them very sparse. So how to do this machine learning algorithm on a sparse and imbalanced data set? We believe there are three ways. One is the data-driven approach. Second is the adversarial scenario generation. Third one, we can maybe embed some knowledge into the scenario generation. We'll look at the first approach using data-driven method. With the data-driven method, here's one example. So there's a lot of already most machine learning is data-driven. Well, in our case, we have interesting approach that will combine two different kinds of data set. So for example, we can combine the safe data set and unsafe or collision data set. And then by extract and embed their latent code, we can generate something that is in the middle of the safe data set and the collision data set. In the self-driving domain, that means the safe data set is something that we collect from the everyday life. It's kind of, we call it naturalistic data set. While in the US and in Germany and in many other countries, they have this collision data set. So whenever the severe accident happen, there is a team of engineer will go to the set and try to reconstruct the collision scene. So we can also have a collision the description of the collision. However, for most of the cases, it's called near misses. Well, the collision is very light, or there's no collision but very dangerous. This is actually what we really want to work on. But however, it's very hard to collect the data because there's no record from the police, and also it's still very rare. So how to do that? So we'll use a conditional VAE to do version autoencoder to do so, and we just add this latent code in a linear way. We use the conditional VAE because the generated scene need to be put back to the road configuration. So the middle part is more like some VAE based art generation that you have a style from one painter and you transfer to another painter's drawing with another painter style. Well, in this case, in our driving case, we still need to stitch to the configuration of the road. So we actually need to be conditional on the road configuration. In this case, not only we can vary the severity between the safe and the risky scenario, we can also put them onto the road configuration. So for example, this is one example that by vary this weight between the safe and the collision data set, we can generate the scenes, we can vary the scenes that from a collision scene to a fully safe scene. So we can generate something in the middle that is a near miss. So how do we extend this? This is the idea, but how do we extend this to multiple vehicles and more complex scenarios? So we'll use a hierarchical learning model to do so. For example, the most challenging, most complex thing is, is shown in this video, that this is a video from Ethiopia, and it is, you can see this is quite complex with big cars, trucks, buses, and pedestrians without a traffic light. So we say, okay, so if we design a car, how the car can deal with this situation? We need to try to model the scene, and we have the belief we can do it because you see, it seems everybody in this city can do this. Can drive and walk safely and efficiently in this situation. So what we do is that, because this is from YouTube, we need to some image processing. One biggest challenge when we design the the machine learning model is the surrounding of the number of surrounding vehicles is time varying for every car. And we need to learn this pattern by using a kind of non-parametric approach. So you can see we do some image processing to extract the information from the YouTube video. And then we are using a Gaussian process to model some macroscopic scene of this image. And also we are using the unsupervised learning, particularly with the hierarchical derivative process with the hidden semi-macro chain to do the pattern recognition. And eventually we identify 6 most typical scenarios in this very complex situation that usually you have a car with another few cars. But it's clear that we can find some major patterns. I believe that's how people can actually drive in this country. So in this intersection. And however, this is purely from the model. We have not specified our downstream task. How to make the algorithm more efficient? We can use the adversarial generative models. So the idea of the adversarial generative model is nothing but you have a scenario generator, and you also have autonomous vehicle that you want to evaluate or improve. So by interact with the autonomous vehicle, you have weights for different scenarios and also some certain directions. To constrain this adversarial, because we do not want to find a scenario that's so rare in the real world that no car can deal with. So we still want we still want to identify the scenario that is risky, but also as common as possible. So with this idea, we use a normalizing flow to generate a very complex scenario surrounding the autonomous vehicle. And for example, this is the pink block represent some cyclist. So we learn this data, the prior from the ArcGoverse dataset, and then we use a reinforcement learning to train the cyclist such that it will behave like a cyclist, but also provide very risky scenario for this autonomous vehicle. So we use this sense to test the 6 different cars trained by 6 different reinforcement learning algorithms. And the interesting finding is that, so if, because most of the time when we evaluate the reinforcement learning, we just random sample from the environment. It's just a Monte Carlo evaluation. Well, when we find out, when we try to evaluate the car or train the car with adversarial scenario generations, we find originally those algorithms behave very similar. And then later on, it shows that when we use the adversarial scenario generators, those 6 different reinforcement actually behave very differently. For example, the model-based reinforcement learning become very stable and still can perform very good. Well, the other the algorithms, some can perform better than others, and some can even get worse as time goes. So that's unveil that sometimes for this safety critical applications, just purely Monte Carlo sampling for reinforcement learning can be misleading. This approach can also be used in purely evaluation testing. So this is a framework that we designed to test autonomous vehicles that in a more efficient way. So that's why we called it accelerated evaluation. In this accelerated evaluation, we will modify the statistics of the surrounding vehicles and such that we can make a safety critical environment. And then we use important sampling to convert the result back to estimate the real performance. And finally, we can evaluate this with some robot in the environment. So this has been used in, for example, MCity, the world's first dedicated testing facility for autonomous and connected vehicles. third one is that we can use the knowledge to generate scenarios. For example, when we try to we can explore some safety critical scenarios, we can generate something that is really unreasonable. For example, if we say if this car is in a tree, then other cars may not see it from the LiDAR. Or if this car is kind of knocking the wall, then other cars cannot see it. We think this is interesting and maybe useful, but maybe not the most urgent scenarios we want to deal with. So to do that, we need to put some constraints. And remember, we have this VAE structure to generate scenarios. Now we can put some knowledge into the latent code to constrain the search space. The idea is this. So our knowledge form a feasible search space. And if the sample is outside this domain, then we project it back to this constraint space so that we can make the search focus on the areas that follows the common sense. In this case, we are using a tree structure to represent the VAE because in this case, we can easily define the node and edges and also easily embed knowledge into the latent code. So one example is that we are trying to construct a very high dimensional LiDAR point cloud scene such that it's a normal driving situation. It looks like a normal driving scenario. However, it's very adversarial to some state-of-art point cloud detection algorithms. For example, in this first case, is a traditional adversarial approach based on point perturbation, meaning we have a scene collected from the real world, then we perturb each point within very small ball. So it is not that effective because most algorithms are robust to this, already trained by, say, randomized smoothing. The second is called a pose attack, meaning we rotate the car. We find when we rotate those cars, many algorithms will fail because they have never seen such a scenario in the real world. However, it's not very realistic because if you rotate the car to all the directions, it's seldom seen such a situation in the real world. And the third one is that we find with certain patterns of those cars, we could attack the point cloud algorithm. So we call this scene attack. We use that to test the 4 state-of-art. Well, now we have better ones. When we published this paper early this year, they're still very top of on the KD dataset leaderboard. And then we found out that our algorithm is actually much more transferable between algorithms, between these 4 point cloud algorithms than other cases, meaning a lot of algorithms, point cloud detection algorithm has not considered such a kind of attack. So this is how we can generate the thing. We can also use the generated scenes to improve our algorithm. For example, when we work on deep reinforcement algorithms, one of the challenges is that the training data set, which is the training environment and testing environment, are not the same. Well, usually the training is in simulation and the testing is in the real world, for example. So how to deal with this situation? Remember this scene we have, right? So we have identified if we want to have a car to drive in this scenario, and we want to adapt it to some situation that has not been covered by the 6 scenarios. What could we do? We can also design task-agnostic hierarchical reinforcement learning for online RL with an infinite mix of Gaussian processes. In other words, we can keep sampling when the car view a scene, if it is already in the model, will recognize and quickly deal with this problem. And if something is very weird, we are using this derivation process to identify, oh, that's actually a new cluster. Then the algorithm will actually launch a new module to learn the new thing. So this actually can be a very effective approach for an online adaptation method. So we test this to on the half cheetah and a self-driving situation. And how to deal with another way of doing generation is that how we can deal with safe RL for robustness. So this has little study on the robustness of safe reinforcement learning. Well, here I want to say the safe reinforcement learning based on constrained MDP, not like a semi-formal method or reachability-based approach. So this is more like a learning approach. So this is a difficult because you can see in this paper we prove this lemma that with in a lot of cases the optimal policy is actually on the boundary of the feasible set. And also the constraints, the safety constraints prevent the algorithm to have a higher reward, But this is not allowable for the safety constraint. So we call this phenomenon temptation, meaning the algorithm, in order to improve their reward, they need to violate the safety constraint, which is actually a very tricky situation. And that's, we think, the fundamental robustness issue for safe reinforcement learning. To deal with that, you can also design a robust RL with the adversarial examples. However, how to get a robust adversarial examples for safe reinforcement learning is not the same as the normal reinforcement learning, because if you train on the normal if you only attack on the reward for safe RL, then the policy will actually not do a good job. However, they will also not violate the constraint. In other words, you cannot learn how to satisfy the safety constraint. So we define two terminologies. One is called effectiveness, that is made the agent unsafe, and also stealthiness, that is made the agent unaware of the attack, meaning we still want the reward to be high. In this case, if we directly maximize, so the maximum cost attack, if we directly maximize the cost, the maximum cost attack is effective, but actually not stealthy. The mean reward attack, which is the first one, is not effective, but also not stealthy. So we found a simple trick, a straightforward approach, but also powerful approach, is that we can maximize the reward so that we can be a stealthy, meaning we can be still maintain the performance, but also violate the constraint. So there is a more detailed proof for this work in these two papers. Finally, when we use robust adversarial reinforcement learning, there are some fundamental issues. So one fundamental issue is that we do not want to construct a too difficult approach that the algorithm cannot achieve. So the way we do this is try to add constraints to the adversarial. The second one is that the training can be unstable because it's a min-max game. So we are using the Stackelberg dynamic instead of Nash equilibrium to design the RARL. So this paper is actually a paper on IJCAI this year. So I will skip the content, and you can check this paper later on. So thank you. That's my talk.